Why use PartBuilder from CAD Enhance? Speed. Create complex schematic symbols in less than an hour. Accuracy. Extract error-free pin data from multiple available sources like BSDL files, IBIS files, FPGA pin reports, existing symbols, and any kind of spreadsheet format you can think of. Productivity. Symbol description language, SmartFrac, and the SDL editor reduce symbol creation time by 5 to 50 times. Reuse and repeatability. Build professional-looking functional symbol libraries. And affordable with attractive leaf space pricing. What makes PartBuilder unique? It provides a system-level re-entrant approach to building symbols for parts. It extracts pin data from a variety of industry standard and vendor-specific files. It allows easy pin renaming and pin type definition and overrides. It has support for pin delays, I/O standards, and any other kind of property you might want to add to your pins. SmartFrac provides upfront pin grouping and sorting functions. There's the revolutionary symbol description language and the symbol description language editor. Flexible property editor to define property values and locations in the output symbol files. It learns your company's property requirements from an existing symbol. FPGA logical flow. Get an early start on easily maintainable FPGA schematics. And continuous improvements. New customer ideas and requirements are welcomed and easily implemented. One of the main keys of PartBuilder is extracting accurate pin data. It reads part pin data from pin report file from a variety of different sources. BSDL files, IBIS files, FPGA pin and package files from Altera, Lattice, and Xilinx. Allegro HDL chip.part file for handoff from an ASIC group. Existing EDA tool symbol files to redraw or convert symbols. And spreadsheets, hand-built or scraped from PDF files. It extracts pin names, pin numbers, pin types, I/O standards, and pin delays. Pin delays can also be appended from separate spreadsheet source. We define overrides for pin names and pin types without modifying the original vendor files. We automatically rename repeating signal pins like power, ground, and no connect as required for replacement on symbols. We automatically identify diff pairs and buses for efficient placement on a symbol. The symbol description language. Back when ICs were small, designers drew schematics of the gates and then the blocks. As gate density increased, new tools were needed to manage the complexity. Hardware description languages like HDL, VHDL, and Verilog became indispensable. As gate density increased, so did pin counts. ICs with hundreds to thousands became the norm. Hardware designers and librarians still create symbols for these parts with inefficient schematic tools. The symbol description language from PartBuilder provides the answer. SmartFrac is a feature of CAD Enhance and it's game-changing efficiency. SmartFrac goes to work after reading the input pin data file. SmartFrac analyzes the extracted pin data and creates SDL template files. The template is a list of all SDL pin matches required to place all the pins for a symbol. Use the SDL editor to organize pin matchers into groups of schematic symbols. So in this case, PartBuilder read the pin description file. It found 85 signal match statements matching 300 signal pins and 24 power match statements matching 905 power pins. That reduces our job when we're creating 1205 pin part to organizing 85 signal match statements and 24 power match statements. The symbol description language and the symbol description file. PartBuilder reads the CAD Enhance symbol description language from the symbol description file to determine how to split up a part into a set of usable signals. The high-level syntax is symbol name definitions with match statements and spacer commands. When we expand that a little further, we can see a symbol name 2 is a locator, a modifier, and a pin match. Some comments, another locator with a spacer, a locator with a pin match, a locator, a modifier, and a pin match. Some more comments, a locator with a vectored spacer, and then a locator with a pin match. And then for a real-world example, here we have DRAM pins where we say on the left I want a diff pair with clock P. On the left I want DQ 7 to 0 bus, and then give me 2 spacers. On the left I want the DQS signal, and on the left with a bubble I want the enable signal. On the right I want to put DQ 15 to 8. On the right, I want to put spacer 1 to 0, 2 spacers 1 to 0, and on the right, I'll put the DQS1, and then the bubble with the enable. Now we end that DRAM pin symbol, and we create a power symbol. Power equals, and we put auto equals VCC, which will plant both VCC pins on both sides of the part. Then we'll create a ground signal, auto equals ground. Notice we don't have to say how many pins there are. PartBuilder automatically finds that for us. PartBuilder symbol description language enables efficient ordering of pins and symbols. It defines symbols in the order of pins within symbols without dragging and dropping. Column-friendly syntax supports rapid creation of STL and spreadsheet programs as well. Symbol name defs wrap around groups of match statements and spacer commands that describe each symbol. The user adds symbols by name without having to track symbol numbers. Match statements control where the pins are placed and what modifiers to apply to pins. Typically we have a locator, some modifiers, and then an equals pin match. The locator is like a left, right, top, bottom, or auto. The modifier is bubble, clock, is pin, depair, pin swap groups, so you can define pin swapping. And then the pin match is a simple or enhanced regular expression used to find matching pins. Spacer commands add spacer pins on the selected side or on both sides. So you can have a locator as spacer, a locator equals spacer vector, and a balanced sim sides plus num spacers. PartBuilder STL supports many loop and variable supports. For I equals 0, I is 10, we have multiple statements wrapped around in an N4. Or we can do a list like 4 banks in 1, 3, 5, 7, 9, and we could do multiple statements using the variable banks. Here's some example match statements. On the right, place all the pins from A control 31 down to 0 in order on the right-hand side, and assign them to the A control pin swap group, which will allow them to be swapped in Allegro HDL. Left bubble, chip select N. Place any pin whose name matches chip select N on the left with the bubble. Top is pin 65 down to 49. Places pin 65 down to 49 on the top, starting with pin 65 on the left. Auto equals ground or both equals ground distributes any pin name containing ground, ground A ground, around the left and right side of the symbol. Left colon D pair AD bus P31 to 0. This matches a bus of diff pairs using either a pre-configured spacing or custom spacing for this match instance. Left vectored ground ADX. For Cadence Allegro HDL, we can create one bust pin for all the ground pins in the part. Some example spacer commands. Left equals spacer. This adds one spacer at the current pin position on the left-hand side. Right equals spacer 3 to 0. It adds 4 spacers starting at the current pin position on the right-hand side. Balance sim sides plus 2. This adds the proper number of pins to balance both sides and then adds 2 more spacers on both sides. It's really used to separate the next group of signals in the current symbol. I like to think of it as creating a sub-symbol within a symbol. We can create STL in a text editor, spreadsheet, or the STL editor. And the STL editor is a powerful editor that's aware of all the STL syntax and allows us to choose sides and create pin matches very quickly. I'd like to introduce the replicate loop construct. The replicate loop is a new STL breakthrough simplifying the creation of loops, building multi-port parts like high-density switches and microcontrollers, or parts with regular banking structures like FPGAs and CPLDs. The user organizes the STL to create one symbol instance. Here we efficiently describe a pair of MGT transceiver banks for a typical Xilinx FPGA. So we can see we create a symbol, MGT Xceivers 128 to 127, and PartBuilder will create that with that name. On the left we'll place diff pair MGT ref clock 128, which is right there. Then we'll put the diff pair bus MGT RXP 3 to 0 128, so that takes care of those. On the right, MGT YTXP 3 to 0 128, we take care of those. On the left we put MGT 120, this is clock 0 128. And then now we separate and do this side of the symbol, MGT ref clock 127, MGT RXP 127, so this is the bank 127 transceiver. And this simple STL creates this beautiful part. With replicate, we wrap the SDL for that symbol with a replicate directive. And this says replicate with change underscore 128 to 126, 124, and it even does ranges, 228 down to 224 by 2, and then take any 127 and replace it with 125, undef, which means it might not exist, 227 down to 225, and undef, and then we end the replicate. So PartBuilder builds a symbol for the original symbol, and then for each substitution, which is this side, provided in the replicate. So in this case, it built 6 symbols and gracefully handled the transceiver slots. So here's the original symbol. Then it built the one with the 126 and 125. Then we built the one with 124, which only had the symbols on the right, or only had the top set of symbols. Then we did 228, 226, and we did 224. So just by taking the original SDL and wrapping it with this replicate, we end up with six symbols which are all the same, except they have the right pin names and the right pin numbers on them. So we have some more simple, powerful loop constructs. SDL enables powerful loop constructs for maximum efficiency. We describe one symbol, tweak it, and then use loops to create multiples, or use loops to group multiple sets of pins in one symbol. It's very effective when building FPGAs and CPLDs due to the structured nature of their pin names. PartBuilder intelligently discards matches for pins and symbols that don't exist, so you can use the same SIM control file to build a whole family of similar parts, like FPGAs and CPLDs from a vendor. In this case, we have a for loop wrapped around the banks A:, B: equals, and then we have an assignment on the left and an assignment on the right. PartBuilder will expand this to it's going to pull out 2 at a time. It'll pull out 0, 1, then it'll pull out 2, 3, it'll pull out 4, 5 out of this list, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. So each time through the loop it takes two of the elements out of that list, so 0, 1, 2, 3, 4, 5, and it substitutes in the first element for A and the second element for B. So that becomes bang 0, 1, PB0 for the A, and PB1 for the B. And it puts the A side on the left and the B side on the right. So it automatically expands it to that, and it creates 8 symbols with 1 bank on each side. So this one loop statement builds 8 symbols, each containing 2 I/O banks for any part in the Xilinx CoolRunner CPLD family. We can also slice buses using the SDL repeat loop. So we could say repeat 4 and end repeat. And then we can do bus numbers, like a bus number 71 to 64, bang decrement 8. This will be expanded to bus number 71 to 64, bus number 63 to 56, all the way down to bus number BN 47 to 39. A SIG 0, Inc. 1 will be expanded to SIG 0, SIG 1, SIG 2, SIG 3, SIG 4. PartBuilder does the work to split the buses into n-bit segments here, and we don't really have to do the math. So in this case, we're going to build a symbol for a DDR bus. So M0, DDR4, DQDS. So on the DDR bus, we're going to have 7 bits of one DQS strobe. Then we'll have 7 bits of data, and we'll put a spacer. And on the right, we'll put the strobe, 7 bits of data, and a spacer. So this is going to expand to, it's going to blow it out to left diff pair P7, and it's going to give us 63 to 56. Then on the right, it'll give us P3, because it started at 3, and it started at 31 to 24, so it's going to start there. The next time through the loop, it's going to have decremented the 7 to 6, so we're going to get a 6, and it'll decrement the 3 to a 2, and then the data will be 55 to 48, 23 to 16, and so forth until we get down to DQS P4 on the left and DQS 0 on the right. And when we look at it, this is what it creates. So it gave us a diff pair with M0 DQS P7 and the group data, 63 down to 56, P6. So with this simple statement, we build this beautiful symbol. The SDL also offers efficient diff pair placement. Diff pairs are automatically identified when reading the pin data with a very exhaustive algorithm. It places 32 pairs of bus with left, we can place 32 pairs of a bus with this one simple statement, left colon D pair, bus name P31 to 0. The SDL diff pair modifier tells PartBuilder to place pins as pairs. We can control the spacing with a default control, which is diff pair default between spacing and diff pair default after spacing settings. Or we can control the spacing of individual match groups with extended diff pair modifier syntax. So we can give a diff pair B plus X, A plus Y, which means the between spacing is X and the after spacing is Y. So let's look at a few examples. Here we say on the left I want a diff pair CSW0RXP7 to 0. So that places the diff pairs CSW0RXP7 all the way down to P0 on the left. And on the right we place diff pair CS0TXP7 to 0. So the receivers ended up on the right, the transmitters ended up on the left with this two simple statements. In this case, the diff pair default between spacing was set to 0, so there's no extra spaces between them. And then the default after spacing was set to 1, so we get this extra space between them, between each diff pair. The next example is if we change the diff pair spacing. So we're going to change the diff pair default spacing equals 1, and we'll change the diff pair after spacing to 2. So we end up with the diff pairs spaced out by double space. So we have one space between the pins, and then we have two spaces between the actual diff pairs. So we can see the separation between them. And here we're going to show, this side we're going to use the default spacing, the diff pair default spacing 0 and 1. But on the left side we're going to actually use the modifier. We're going to say we want B plus 1, which will put an extra space between the diff pair elements, and A plus 2, which gives us the equivalent of that side. The IsPin modifier in SDL is very powerful when building a TQFP or DIP SOI symbol, and you want to build it the way the symbol looks on the package. So with this simple thing here, LTC 2975 equals left is pin 1 to 16, bottom is pin 17 to 32, right is pin is 48 to 33, and top is pin 65 to 49. And that builds this symbol. So it read the pin data, it knows that pin 1 is vsense P0, so it builds the part and it just puts pin 1 to 16 on the left, like we said, pins 17 to 32 on the bottom, pins 48 to 33 on the right, and pins 65 to 49 on the top. So we designed and built this part in under 30 minutes while still manually extracting the pins from the LinearTech PDF file into a pinnum type file. Let's say we don't like the top and bottom pins. We want to split that into two symbols. So we'll change that. We make a slight change in the SDL where we end the first symbol. We rename the one LTC 2975 left right. So on the left we'll put is pin 1 to 16. On the right we'll put pins 48 to 33. But now we're creating a second symbol by just starting a new symbol with the top bottom. On the left we're going to put pins 17 to 32. On the right we're going to put pins 65 to 49, and then we end the symbol with the semicolon. And that creates these two symbols where we see the 1 to 16 on the left, 48 down to 33 on the right, 17 to 32 on the second symbol, 2 of 2, and 65 to 49 on the third. So we tweak and change these symbols in under 5 minutes. The SDL IsPin modifier can also be used to create connectors, using the IsPin modifier to draw a large DRAM connector. So this is all the SDL it takes to draw a connector with 288 pins. On the left we're going to put pins 1 to 72, on the right we're going to put pins 288 to 217, and that's the top half symbol. The bottom half we're going to put 73 to 144 and 216 to 145. That's going to create these two symbols, 1 to 72, 288 down to 217, then 73 down to 144, and A2 down to 145. So now we'll tweak the SDL to break the top-bottom symbols to show more like a real connector where it has a notch between pins 77 and 78. So what we're going to do is we're going to move pins 77 and 78 over to this pins 73 to 77 back over to this symbol. So we change it and we say on the left pins 1 to 77, on the right 288 to 212, the left, and then in the bottom half we do 78 down to 144, and on the right we do 211 to 145. So this connector was built in 35 minutes. We used the free online Nitro Cloud to convert a PDF to a spreadsheet from the Micron datasheet. We used the generic CSV flow of PartBuilder. We defined the generic CSV file fields in about 5 minutes. We used Pin Explorer to assign the pin types in about 10 minutes. We define and assign the properties for the part in about 5 minutes. We created the SDL in about 5 minutes, and we generated the part in about 5 seconds. Then we tweaked the SDL to split the symbols at 77 instead of 72, and then we regenerated the part in another 5 seconds. Symbol count limits in PartBuilder. PartBuilder automatically splits matching pins across multiple subsymbols if the number of pins exceeds a programmable limit. Let's say you have 200 ground pins named ground and the symbol pin limit is set to 150. PartBuilder will split ground into 2 symbols, with the first symbol containing the first 150 pins and the second one with the remaining 50 pins. The symbol pin limit may be overwritten per symbol name using the sim pin count override control, or just globally with the symbol pin limit. So PartBuilder can use existing library parts to configure property content and locations. We could choose symbol files from a reference library symbol to extract part property intelligence. The prop temple symbol file determines what properties are included in the symbol and their locations relative to the top, center, and bottom of the symbol. The prop template PTF file chooses the PTF file, this is in Allegro HDL, and whether the properties are key or injected. And the prop template chips file determines which properties will be included in the chips.part file. It's a little simpler for OrCAD, PADS, DX Designer, and Altium. So it lets us pick the files as a template. We use the button to read the property templates, and then we open the part property editor. The Edit Part Properties button pops up a window allowing the user to set the values, locations, visibilities, and text parameters of the part properties in the symbol, chips.part, and PTF file. It's very easy to manipulate property values, locations, and inclusions in the symbol and part file. We use an anchor system, so we can anchor and an offset. So we locate a property by anchoring it to the bottom and providing an offset. We can control the visibility, the justification, and the size of the text. And all of these can be learned by reading the template files. In closing, PartBuilder is an efficient, accurate add-on tool which automates building schematic symbols for low, medium, and high pin count electronic devices for the Allegro HDL, DX Designer, OrCAD, Altium, Eagle, PADS, schematic connector tools. PartBuilder's symbol description language makes placing pins across symbols and reordering and spacing pins within symbols an easy task. Engineers and librarians can quickly build parts with multiple symbols and then tweak them so they work best when connecting parts in the schematic. PartBuilder control file structures enable efficient reuse between common part types. It can read an existing symbol from a customer's library to extract the intelligence, including which properties are embedded in a symbol, the formats, locations, and visibility of those properties. PartBuilder establishes a professional standard look and feel for your symbol library. Thank you. To start building your first library part at the speed of CAD Enhance, please visit us at www.cadenhance.com to download PartBuilder and request a free evaluation license. Appreciate your listening.